First of all, I would like to thank organizers for the possibility to give a talk at this conference. Thank you very much. So my talk is about quantum SLN invariants of knots. They are also known as Racah-Turaev invariants or colored Homfli-Petit invariants. Well, in my talk, I will tell you about two approaches how to construct them. I will tell you about some problems in these constructions, some advantages and disadvantages of them, and about some of our particular new results about computational of these invariants. So let me start from the first approach, which is known also as the Racah-Turaev approach for constructing quantum invariants. In my talk, I will assume that I consider only knots, not links, but absolutely everything can be straightforward generalized to links also. Let me consider some knot K. It is very well known that it can be represented as a closure of some braid. So let me have a braid with M strands. And I put here some orientations. It will be goes from top to the bottom. And I have some crossings between adjacent strands. Something like that. And I assume that I have a closure of these braids, but I will not draw it on the blackboard. So this approach implies, actually this approach is based on idea to use a quantum R matrix to construct invariants of knots. So we associate with each strand irreducible representation of quantum universal enveloping algebra of the algebra SLN. And since I consider knots, I associate with each strand just one and the same representation R. These representations enumerates by Young diagrams. And also we slice our picture at each crossings, and we associate with each crossings quantum R matrices. So with crossings between first and second strands, we associate R1, then R2, and so on. So if I have M strands, then I have Rm minus 1 different R matrices. So, and quantum invariance of a given knot of a given representation R is equal to the sum over representations Q trace over R matrices R1 in power of A1, depends on Q, times R2 in power A2, and so on, times quantum dimension of representation Q. So what is written here? So I have a particular knot, and I have a particular order of crossings into my brain. So, and I associate with each crossings R matrices, and actually their ordering and these numbers, A1, A2, and so on, they actually encode me my knot. So, since in my talk it is not important which particular knot I consider, that I just don't care about this particular order, just write here very schematically. But what is important? It is important that this R matrices depends on representations Q. Q, it is the following. So since I have M strands, then I have m tensor product of representations, and I decompose them into a sum over all irreducible representations Q. It is a finite sum, and here I have a sum over all such terms which appears in this product. Well, let us consider the case when m equals to 2. Then what I have? In this case, actually, I have just two braids with some crossings n. I associate two representations R. And I have only one R matrices R1. So my formula took the following form. In some power n. So how to find this R matrix? Actually, it is possible to choose basis on this space in such way that this matrix becomes diagonal and fully determined only by its eigenvalues. These eigenvalues can be easily computed as follows. It is equal to the Q in power kappa x alpha. Alpha goes from 1 to some m capital. X alpha, again, it is a decomposition of tensor product now of two representations, because now I have two braids. And kappa, it is a famous function on Young diagram. It is actually eigenvalues of quadratic Casimir operator. It can be written as j minus I, sum over all I and j, where I and j, it is a coordinate on my Young diagram, which represent my representation. So, actually, with the help of this function, we can easily compute quantum invariance for any irreducible representation R for such part of node, for such class of node. But actually, it is a rather poor class of node. It is a subclass of torus nodes, which are known as 2, n nodes. Let us consider the next case.
Can I ask a question?
Yeah.
So I think that there you probably should have only the eigenvalue, but not the trait, because in the trait you also have one dimension there already. Right? I mean, in the formula.
Yeah, in this formula. Yeah.
No, the very first one.
Is it? Yes.
Say for example, if the braid is a trivial braid, then there, when you take the trait, you have there only one dimension, and you multiply by another quantum dimension here, so it's kind of strange. You should have only one quantum dimension, right?
Yeah, I have only one quantum dimension, this one.
But when you take the trace,
This trace, it is just a matrix trace. It is just ordinary trace.
yeah, but if the braid is trivial, when we take the trace, then you have just the dimension.
Yes, and this reduces just, it will be a sum over dimensions.
The square of the dimension.
Yeah, and it is natural answer for unknown in this approach. Yes, it is correct. Okay, let's consider the case when n equals to 3. Then Now I will have 3 strands, and now I will have one more R matrix, R2. So this is the answer how to compute it. Actually, since they are R matrices, there is one equation on them, which are very well known Young-Baxter equation. Actually, in a general form, can be written as follows: Ri times Ri plus 1 times Ri equals to Ri plus 1 times Ri times Ri plus 1. And so since I have already can compute this matrix, then I can try to solve this equation to get a solution for R2. But actually it is an extremely complicated system of nonlinear equations, and it is very difficult to calculate them. Actually, as far as I know, it is possible to do in general for such cases only when rank of matrices less than 6. In a more general case, it is, so actually I don't know how to compute it. But in this case, we can use representation theory to compute R2. It turns out that R2 now is rotated with respect to R1 by some matrix U, which is a very well-known object in representation theory, and it is known as quantum Racah matrix, or matrix of quantum 6G symbols. Well, let me define it. Suppose that I have 3 representations, R1 times R2 times R3. I take such tensor product and I fix some resulting representation R4. And let me take this product in the following order. First I multiply R1 and R2 and then R3. And then let me consider another ordering of multiplying my representations with the same resulting representation R4. Then, if I fix orthonormal bases in these representations, then I will get some basis induced by this choice in these representations R4. And these representations R4 actually are same representations, like vector spaces, but their basis will be not the same. One basis will be rotated with respect to another basis. And this rotation is described exactly by Racah matrix, which determined by 6 representations. So R1, R2, R3, and R4, and by X and Y. X, it is representations in the composition of these two guys, and Y, the composition of these two guys. So this is my Racah matrix. So, and then, in a such form, If I manage to compute Racah matrix, then I manage to compute second R matrix R2. However, in this formula, I need to sum over all representations Q. Actually now Q, it is nothing but R4. So if I use this approach, if I want to calculate representations, quantum invariance at some representation R, then I have to consider tensor cube of representation R, and I managed to calculate Racah matrices for all terms which appears in this sum. Well, actually it is rather tedious and rather difficult to do it. For example, if I consider first non-symmetric representation, like 2, 1, then in this case I will have 22 terms in this sum, and 4 of them will have 4 matrices will have a rank greater than 6, greater than 5. Sorry, 2 of them will be matrices 6 by 6, 8 by 8, and 9 by 9. So for representations 3, 1, we will have already 48 terms, and non-trivial will be 26. Rank of these matrices will be in a range from 6 by 6 to 20 by 20. So actually, it is a big disadvantage of this method. So I have to calculate a lot of such Racah matrices if I want to calculate quantum invariance. But advantage of this method is that Racah matrices U do not depend on rank of my group N explicitly. It means that I can fix N at some value and calculate Racah matrices for this value, and then this result will be correct for all N which greater than my given value. So, well, actually I want to note that first non-three-strand node is a 6, 1. It is a node from a standard classification table, also known as the Royston table. 6-1 means that it is a node with 6 crossings. In a minimal representation, 1 means that it is just the first node in this table. So this class of node much richer than the previous one, but it is still rather poor. Actually, we have an infinite number of parameters now here, but still they are in some sense just of two types. I can have crossings only between first and second and third, and so on. So this is a first construction. Let me briefly consider the another construction which allowed me to calculate quantum invariance for so-called arborescent nodes. These nodes can be represented by a tree with n-valent vertices. Let me draw it, for example, so actually it can be any tree of such form. So in this tree, any edge, it is a 4-strand braid with 2 parallel and 2 anti-parallel orientations on strands. Just for example, this one, or this one, or any other possible combinations. The only thing which I need to care, it is just about self-consistent of the whole picture. Then, let me draw, for example, this part in detail. So how, oh, sorry, I forgot to say that vertex in this tree, it is just a connection of these 4-strand braids without intersections. Let me draw this part in details, then it will be clear. So suppose that I have a 4-strand braid. Suppose some orientation. And then I can have any crossings between adjacent strands. So this is my vertex, this part. And here I can have any crossings. Oh, and so on. So with these crossings, we associate some matrices, which are actually also some analog of Racah matrices, which our matrices which we used in the first construction, but we will denote them here as T and T bar. T bar stands for such strands which have opposite orientations. T stands for such strands which have same orientation. For such crossings which appears in the center of this braid, there we will have a matrices which also rotated with respect to the matrices T and T bar. With the help of matrices S and S bar, these matrices are also Racah matrices, but of a different type. Actually, they correspond to representations R adjoint, and R adjoint, matrix S and S bar for R adjoint. So for some orientation, I associate representation R, but then in this strand for another representation, another orientation, I should associate representation R adjoint. And then it turns out that in this construction, any possible Racah matrices can be reduced only to these two types, S and S bar. However, the answer for quantum invariance of such node will include only two such Racah matrices. Not any possible number of them, like in the previous construction, but only two of them. Let me write it very schematically. So let me call this leaf just like fx, and then in this formula I put some such fx's. Let me denote this part like some propagator p x and y times p x y and times some other fingers f4 and, for example, f5, and some are over x and y. So the picture corresponding to this formula, it is just such tree. So f1, f2, f3, f4, f5, and here I have p. So with the help of such building blocks, I can calculate quantum invariant for any such node and link. So, and I want to stress that in this calculation I use only two types of Racah matrices. So if I want to calculate such quantum invariant, then I manage to calculate only two Racah matrices. So this is advantage of this method in the contrast to the previous one, where I have to calculate a lot of Racah matrices. But disadvantage of this method is that these Racah matrices depends on the rank of my group explicitly, because here I have a joint representation. So it means that I cannot fix some particular n and calculate Racah matrices for this particular n. So I have to calculate these Racah matrices for several values of n and find an analytical continuation of them. So it is rather difficult to do it. Well, so some particular results about this construction is that in 2013 by Satoshi Nawata, Ramadevi, and Zodin-Mavia, they calculated Racah matrices for all symmetric diagrams, when my Young diagram is just one row. In 2014, Gu and Jokers calculated Racah matrices for first non-symmetric representations 2, 1, and in this year we managed to calculate representations 2, 2 in this construction. Well, now well, actually the first non-arborescent node, it is a node of 818. So definitely this class of node is much richer than the previous one, but also, for example, we cannot cover all nodes in, for example, Royston table. Even if we combine these two particular constructions, then we cannot cover, for example, Racah table and more. So, but it turns out that it is possible to join these two constructions. Let me draw a tree-strand node. So, and let me redraw this picture in the following way. So, here now you can see that I have exactly a 4-strand braid like in this picture. And it turns out that now I can insert here any such fingers, F. Or moreover, actually I can insert here any such tree. Just I can cut some strands in some place and just insert it here. Just the only thing which I need to care, it is just a self-consistent of the whole picture. It is the only restriction. And then, with such trick, it is possible to calculate more nodes than separately with these approaches. Actually, this class of nodes, at the present moment, we do not know which node belong to this class or which node, because any node which we have, we manage to redraw in such a way. Actually, it is rather a huge class of node. But I am absolutely sure that, of course, it is not a general construction. Not general node can be represented in such way. Well, and the last result which I want to mention, it is some kind of relation between U matrix and S matrix. It turns out that there is one class of node which is simultaneously a tree-strand node and arborescent nodes. It is the following class. Let me have n crossings here, -1 crossing here, n crossing here, and -1 crossing here. And it is exactly a very well known pretzel node of the following type. So it is a tree-strand braid representation, it is arborescent representation. In terms of arborescent pictures, it is just a one vertex with 3 leaves. And now, if I write formulas for this class and with the help of first construction and for this picture with the help of second construction, then I will get the same. Then I will get the following. So I will have some some order representations y and z, some matrix H, y, z times lambda y in power of m and lambda z in power of n. This is for this formula can be obtained with the help of first construction. This matrix can be computed with the help of Racah matrices from the first approach, and lambda it is nothing but eigenvalues of quantum R matrix. So, and if I write the right hand side, then schematically I will get something like that. So this guy K comes from this part, and these guys comes from this part, which are actually same as this part. And now, comparing left hand side and the right hand side, we get the following. In a matrix form, I can schematically write it like H times S equals to K times S. So matrix H can be computed with the help of Racah matrices from the first constructions, with matrices U. S is a matrix of the from arborescent picture. It is another Racah matrices. And this very simple equation helped me to calculate S matrix with the help of U matrix. Actually, we get some sort of relation between two different objects from representation theory with the help of knot theory, which is rather interesting and very unexpected. That it is possible to calculate one matrix with the help of another matrix. So, and if I know S matrix, then it is very easy to calculate S bar matrix with the help of linear equation, which are actually analog of Young-Baxter equation for S and T matrices. So, actually, this is the way how to compute for example, S and S bar matrices for cases of so-called multiplicity free. It is in terms of the Venn diagram, it means that we should consider only diagrams of a rectangular form. So, when we consider not rectangular form, actually this case is more involved, and now it is not very clear how to do it, but I think that it is not very difficult to generalize for any case. So, and actually this was our way how we constructed S and S bar matrices for representation 2, 2. Well, probably I would like to finish at this point. Thank you very much for your attention.